Welcome. So in this week's Digital Office Hour, I thought we talk about the ARMA model. So we talked about the ARMA in the CRAM 1 lecture, and I felt that I wanted to give you a quick tutorial on applying what we talked about to a specific ARMA model, and here the ARMA 1.1. Yeah, so it will be about how do we estimate an ARMA 1.1, how can we use that model to make a forecast, and how do we quantify the accuracy of these forecasts. Yeah, so here is what we are going to do. As I've said in CRAM 1, we will not rely on numerical optimization, but only on methods like ordinary least square, for which we have the solution right away. So therefore, we will review the two-pass estimation approach to fit the ARMA to data. We will do that within our training set. Then for our test set, we will forecast the next two outcomes, and we will also quantify the accuracy of these forecasts. So let's just do it. I've already prepared the data. Yeah, so here's our setup. Think about it. We have some time which goes from 1 to capital T, and we have some variable xt. Might be a return, might be GDP growth, unemployment growth, inflation, whatever. Yeah, some stationary time series. Now, what's the goal at this tutorial? As I've said, first of all, we want to fit that xt for our training set to an ARMA 1.1 model. The second thing, once we have done that, is we now want to make a forecast for t plus 1 and t plus 2. Yeah, think about t is the last observation in our training set, and therefore that will be our first forecast for the test set t plus 1 and here t plus 2. That's just about a forecast, and now we also want to quantify the uncertainty around that forecast. Right? We all do that using the ARMA 1.1, so it gives us a nice application to play around with the concepts from class. Yeah, that should be familiar to all of you, but nevertheless, I hope it's useful. Okay, so let's just see what we have. Okay, let's go to the solution. We are talking about one first, and that is the fit. We don't want to use numerical optimization, therefore we won't use maximum likelihood, but instead we use the two-pass estimation. Yeah, because that allows us to rely only on least square methods, for which we have a closed form solution. Okay, so here is how we start. We want to fit the ARMA 1.1. So think about, we've already determined that the order that we care about for the AR part is 1, and MA part has also the order of 1. That's kind of where we start off, because I've already specified that we want to work with the ARMA 1.1. Yeah, we talked about in class, you can use portmanteau test, you can use the AIC, the BIC, or the PACF test in order to pin down the order. So that's done. It's not the task of this tutorial. Maybe it's another one. So we rather want to go to the ARMA 1.1 directly. So we know what's the data generating process for the ARMA 1.1. Well, we start with our standard notation xt, let's say the return, and xt has a predictable part as of t minus 1, and then there's an unpredictable part, epsilon t. Now epsilon t, it needs to be a white noise process. Yeah. We don't say it needs to be Gaussian white noise, just white noise. IID white noise. Okay. Now that is just our standard DGP, and now the mu t minus 1 in the ARMA model assumes a specific structure for the predictable part, and that would be phi 0, so I incorporate a constant, plus phi 1 times xt minus 1 plus theta 1 times epsilon t minus 1. Right, it's xt predictable part as of t minus 1. And there you see that is t minus 1, that is t minus 1. That's the ARMA 1, 1. In general, that is measurable as of t minus 1. Okay, great. Yeah, that's the AR part and that's the MA part. These ones are not important, not necessary here. I just incorporate that. Nevertheless. Okay. So how does the estimation work? Right. As we said in class, we now use this two-pass estimation. If I cannot run a maximum likelihood jointly, I have to go step by step, which means pass number 1 will be we pin down the AR part, the phi 0 and the phi 1. How do we do that? We are basically fitting an AR1 to our training set xt. So these are linear models, they are linear in the parameters, therefore they are all a special case of our linear representation. So what's the y here? Y will have dimension t minus 1 times 1. So our y will be defined, it will be let's make it like that. It will be the second return, the third return, all the way down to the tth return. The dimension is therefore t minus 1 times 1. Now what about the x? Now the x, we fit in AR1, we want to estimate that coefficient and that coefficient here. Therefore the first column will be a 1 and the second column will have the AR structure of order 1, therefore we regress the second return on the first return. Or here the third return is regressed on the second return. All the way the tth return is regressed on t minus 1. Yeah, so the dimension will be t minus 1 times 2. And from that, it's now obvious that the beta, the parameters that we care about, will be here the phi 0 and the phi 1. Yeah, will be phi 0 and here phi 1. Dimension 2 times 1. So we have t minus 1 times 2, and here we have 2 times 1. And what's the nu? I just use the nu as it's my measure for the error. It will also have t minus 1 times 1. Okay. So what does that tell us now? That tells us we could apply ordinary least square. Let's assume the OLS assumptions hold. Yeah. Therefore, we apply OLS. And now we have that the OLS solution is just that standard expression x prime x minus 1 x prime y. And in our problem, that will give us precisely our estimates phi 0, OLS and phi 1, OLS. That's how we determine these coefficients. Now, what about the errors? These nu, the OLS estimate for nu will be our y minus x beta OLS. That will be t minus 1 times 1. For the x up here, it is t minus 1 times 2 and the beta, so it all works out. So we have t minus 1 times 1. So far so good. Now the did we say? That is pass number 1. Yeah, we were fitting the AR1 part, we got these coefficients. Now it's about pass number 2. It's an iterative estimation approach. So we are now fitting an MA1 to this new OLS. This one here. Okay. How do we do that? Well, again, the MA1 can be written here as a linear problem. Yeah, so again, we write down the expression for the linear model plus epsilon. Now, what would be the y in that case? Well, the y in that case, again, it's an MA1 structure. So we want to find out, or we want to regress the nu of a specific time period on its leg. Therefore, we take that nu 2, and then here is the nu OLS, comma 3, all the way down to nu OLS, comma t. Therefore, here again, dimension is t minus 1 times 1. And now we regress that on the x. Now there is no constant in the MA1 because the nu already has an expectation of 0 by construction, because we have a phi 0 in the path 1. Therefore, here we only regress on the past leg of the error, which means the second data point for the error will be regressed on the first data point, or the third data point will be regressed on the second, and the teeth will be regressed on the t minus first. So we have t minus 1 times 1, the dimension. And it therefore turns out that the beta here will be our theta 1. Okay. Therefore, again, assuming the OLS assumptions hold, we can now determine the beta OLS, which will be, as it was said, just a theta 1 OLS estimate. And that is now nothing else than x prime x to the minus 1 x prime y. All right. And what about our errors? Our OLS error is now nothing else than y minus x. That's already used the theta 1 comma OLS notation. Yeah, so we have here t minus 1 times 1. That is t minus 1 times 1, and that's a scalar. So wonderful. We see that the estimate for the epsilon will also have a t minus 1 times 1 dimension. And what do you do now? Now what you should do is you should check that epsilon OLS is IID white noise. Right? So what you could do is, for example, I would do the following. So let's say it should be white noise. Of course, the drift, it will be 0, and it should have a constant variance, sigma square epsilon. For example, we know that sigma square epsilon, the estimate for that, yeah, let's say the OLS estimate, is nothing else than, well, we just take our OLS estimate for the epsilon, transpose epsilon OLS, that now becomes a scalar. And now we divide that by t minus 3. We've estimated 3 parameters, so therefore we divide by t minus 3. So that's now an estimate for the variance. Therefore, what I would do is I would take the epsilon all s series, right? That is of dimension t minus 1 times 1. I divide that by sigma square epsilon all s, and now I test whether that thing is n01. I could use a Jacques-Barra test, for example, which tests whether that random variable here follows a Gaussian variable, and if that was positive, yeah, if the Jacques-Barra test, for example, tells me I cannot reject the hypothesis that that ratio is Gaussian, then I would know that the epsilon OLS, which I estimated, it indeed would be even Gaussian white noise. Not just white noise, but it would be Gaussian white noise. Drift 0, and the estimate for the variance would be this one here, which we've just determined from up here. Okay, but here the task was to fit the ARMA 1,1, so we assume that epsilon is indeed white noise, even Gaussian white noise, but still you should check that always explicitly. So what do we do next? Well, to sum up, we have used basically our training set to pin down the ARMA 1,1 coefficients of that xt process. Right, so we have basically now determined that xt equals phi 0 all s. We determined that based on path 1. Also based on this path 1, we got the first slope coefficient times xt minus 1. Path 2 allowed us to identify the MA part, which is now epsilon t minus 1. And then we have plus epsilon t. Right, and we had that our t was element in 1 up to t. Okay, they were all determined by all s, these coefficients. Okay, now you can also now get the standard error or the t-statistic of these parameters, use the OLS counterpart, but keep in mind the true standard errors are larger because we have applied this two-step approach, and the standard errors that you would determine, let's say the standard OLS standard errors, would assume you estimate all at once, which we haven't done. But it's a lower bound at least. Gives you still an indication of the significance of these parameters. Now we go to goal number 2. Goal number 2 was forecasting. So now it's an exercise on how do we make forecasts with the ARMA 1,1 structure. Right? So we want to forecast t plus 1. Or to be more precise, we want to forecast what is x t plus 1 if we can condition on ft, on all the information up to time t, capital T. So now what does it mean? We want to forecast. We are interested in what is the conditional expected value of that thing here. That's our last observation within the training set, which we used. We used the entire training set to pin down the parameters, and now we want to make a forecast for the future, next period. Okay. Now what that is, we just use our standard notation. That is nothing else than what is xt plus 1. That is our mu t plus epsilon t plus 1, and now we condition on ft. Yeah, keep in mind, as I explained in lecture, that is measurable as of ft. Here you see why it's advantageous, because we conditioned on ft. That is a constant as of ft. Epsilon t plus 1 is white noise, So the expectation is 0, and therefore that is just mu t. Okay, now given that we are working with an ARMA 1,1, we have assumed a special structure on the mu t, and that special structure will be that we've already estimated our constant using the training set. We have the AR1 part, we've estimated already that coefficient, times, now you see it's the as of mu t, so it gets multiplied by the xt, it's still ft measurable, so that variable is known, plus, and now we've also already estimated our ma1 part, which gets multiplied by epsilon t. Again, as of ft, I know epsilon t, so it's observed. I can treat that as a constant. Okay, so that will be my forecast. Now, let me already do goal 3 for the t+1 forecast. Let's already talk about the accuracy. The forecasting accuracy. Okay. Well, I know that the realized value will not be xt, will not be my forecast. So what I can do is I can assess the accuracy by specifying what is the variance of xt plus 1 conditional on ft. That's a measure for the uncertainty around my forecast. Well, again, we start with our standard notation. Now, what is xt plus 1? That will be the predictable part, mu t plus epsilon t plus 1, and now I condition on ft. Again, here you see why that makes sense, because as of ft, mu t is known. So there's no variance around that one, no conditional variance. So the only variance comes from the variance of epsilon t plus 1 as of ft. Now epsilon t plus 1 we assumed is white noise, IID, with a constant variance, so therefore that thing is just sigma square epsilon. It's a constant. Right, that's our uncertainty. Now we can say that is roughly speaking, we've already used the training set to pin down an estimate for that. So that is roughly 1 divided by t minus 3 times what we called above epsilon OLS, epsilon OLS. Yeah, that would be the approximation for the variance. Now, if the epsilon is Gaussian white noise, as shown above, if that is a Gauss, then we have that the probability density function of my xt plus 1 condition on all the information up to ft, that will then be a Gauss variable where the expectation is that and the variance is that. So you see that we just determined the conditional expected value up here. Everything is known as of xt, coefficients are estimated, and the variance is also as of ft is also known. So now we specified the full uncertainty around our estimate based on the variance, but we now have a full distribution for our one step ahead forecast. Yeah, if the epsilon is Gaussian white noise. Okay. So I also wanted to talk about the two-step ahead forecast. There we will rely on the law of iterated expectation, which I did not explicitly mention in class. So I want to do that now in this tutorial. So we are going back to objective 2, and now it's about forecasting xt plus 2 with using only ft variables, information up to ft. So we want to forecast that. So here's how we do that. For forecasting, again, we want to know what is xt plus 2 as of today. So it's a 2-step ahead forecast. Well, first of all, instead of writing it like that, I want to write it like that. That's no big deal. All right. Now here comes what I haven't mentioned in class explicitly. I want to use the law of iterated expectations. Now what's that law saying? Well, it just says that the conditional 2-step ahead forecast is just the same thing than that thing here. So you see, all I need is a sequence of 1-step ahead forecasts. Makes life easier. I basically build that forecast, which is a 1-step ahead forecast. I've already done that in the exercise above. And once that is known, I take again a 1-step ahead forecast. Okay, that's a trick you should always remember. It's really useful. Okay, so let's keep using our notation. That remains as it is, conditional as of cap t. And now we want that forecast as of t minus 1, which variable xt plus 2. Now again, we use our notation. What is xt plus 2? It has a predictable part, mu t plus 1, plus this unpredictable part. Okay. So now again, as of t plus 1, that is known, while as of t plus 1, that is a IID white noise process with mean 0. Therefore, it simplifies to that expression. And we've already determined what the 1-step ahead forecast looks like. But let's just do it step by step. Next thing we do is now we specialize to our model. We have an ARMA 1-1, so we have a special structure on our mu, which we now need to exploit. Therefore, we want to get the conditional forecast. Now, what is mu t plus 1? In the ARMA 1-1 world, we have a constant plus a slope coefficient for the lag as of t plus 1. That's the forecastable part, therefore the lag is as well t plus 1. And then we have the MA1 lag, same measurability also as of t plus 1. Alright, but now we have the condition on t here. Now what do we see? That is a constant. We put that out of the expectation. That's a 0. That is a constant. And now we have that plus theta 1 times epsilon t plus 1. That is again, epsilon is white noise, the expectation is 0, so the entire thing is 0. Okay, now we have to express xt plus 1 as of t. So that is what we are doing here. Okay, let's do it like that. So we are just writing in what we want. So what is xt plus 1? Well, that thing is an ARMA process, ARMA 11. Therefore, we have a constant here plus the slope coefficient of the AR part, which would be xt, plus we have an MA1 part, which is the epsilon t, and then we have the noise part. As of t plus 1, it's noise, so it's epsilon t plus 1. Okay, so what do we have? That is known as of ft, that is known, everything gets out. Again, white noise, epsilon, the expectation of as of t of epsilon t plus 1 is 0. So that part is 0. All the rest is a constant as of ft because I condition on capital T. Capital T is known, everything is known. So therefore I just group terms. I have here phi 0, 1 plus phi 1, that thing here. I have phi 1 square times, that is now known, I can put that out. And then I have, although this is white noise, again, but you condition on capital T, so that thing is now observed for you. It's therefore known, therefore we have phi 1 times theta 1 times epsilon t. Right, so just again, what did we do? That is just the expectation of xt plus 2 conditional on ft if xt follows an ARMA 11 process. So that is good. We have seen that exercise now of law of iterated expectation. And what we now want to do is we want to talk about the precision of that forecast. So at goal number 3, it's the accuracy of that forecast. Okay, now how do we pin down the accuracy? We would again look at the variance. What is the variance of xt plus 2 if we can condition up to today? Okay, now by definition the variance is nothing else than the squared deviation of the realization from the expectation. Yeah, that's the spread in the realization from expectation. It gets squared. We take the expectation. The expectation needs to be as of t. Yeah. And therefore it's the conditional squared deviation from the mean. Okay. Now what do we have to do? Now that is what we've already determined above using law of iterated expectation. What we now need to do is we need to express xt plus 2 as a function of just xt. Yeah, again, as something which is measurable as of ft, then the expectation part will cancel out. We end up with as of ft only random variables. We square them. There's white noise. The squared part will depend on white noise only, so most likely something with sigma square epsilon will show up. So therefore let's just do it. For that we will just note that xt plus 2 is what? Well, again we work with the ARMA 11 assumption. Therefore we have a constant plus a slope coefficient with regard to the first leg, and then we have our MA1 part, and we have our Gaussian white noise, or just our white noise process, plus 2, right? Okay. So again, just for completeness, that would be our mu t plus 1, and here's our random variable. As of t plus 1, that is the random one. Okay, now you see what we have to do is we need to re-express here xt plus 1 in terms of xt, because we want a condition on ft. Yeah, so everything must, all the x's must be in terms of ft. Therefore, we are just writing phi 0 plus phi 1, and now again we use the ARMA 1,1 structure for that part here. Yeah, so maybe let me already put the parent brackets here. I already write in that part here theta 1 epsilon t plus 1 plus epsilon t plus 2. Okay, now we just work on the ARMA here. Again, constant plus slope plus ma1, same thing here, epsilon t, plus the error, which would be t plus 1. Alright, phi 1 is out, and now it's the ARMA structure, predictable part, unpredictable part as of t. Okay, that's correct. And now we're just collecting terms. Yeah, so we have phi 0, 1 plus phi 1 plus phi 1 square xt. We have phi 1 theta 1 epsilon t plus we have epsilon t plus 1 times phi 1 plus theta 1, and now we have epsilon t plus 2. Okay, yeah, that is our xt plus 2. Okay. Okay. Now we go back. In order to get the variance of xt plus 2, we need to get xt plus 2 minus the expectation, and that must be squared. Okay, so what we have, what is the expectation? Look here. That part, I've seen that already in xt plus 2. I've seen that part in xt plus 2 and that part. Let's just check. That is part of the expectation, part of the expectation, part of the expectation. So it cancels out. What we therefore end up with is just the expectation of the lower part here of epsilon t plus 2 plus epsilon t plus 1 times phi 1 plus theta 1. That entire thing gets squared deviation. Okay, wonderful. Now, what do we have? We have the expectation of epsilon t plus 2 square plus the expectation of, I can put that out, it's phi 1 plus theta 1 square, the expectation of t plus 1 plus twice phi 1 plus theta 1 times the conditional expectation of that. Now that thing here, keep in mind, is 0. Why? Because it's the expectation of that times expectation plus the covariance. Since it's white noise, there's no co-movement, no predictable co-movement between t plus 1 and t plus 2. That is what white noise, it's one feature of white noise. So that entire stuff here is 0. Now that stuff, what's that? Again, it's white noise. So there's no predictability in white noise. Therefore, the variance is just sigma square epsilon. The same thing here, it's just sigma square epsilon. And therefore, the entire variance is sigma square epsilon times 1 plus phi 1 plus theta 1 square. Alright, just Let's use a different bracket here to make it consistent. So you see, if it was an AR1 forecast, then the variance would be sigma square 1 plus phi 1 square. Now it's an ARMA, so you ARMA 1 1, so you still have the MA part, and this gives you that additional theta 1 here. Okay. Therefore, what do we have? We therefore have, again, if the epsilon is Gaussian white noise, then we now just derive that xt plus 2 as of today, as of ft, that will follow a Gaussian variable with the mean, that's our forecast. It's like that. We've determined that from above. And the measure for the uncertainty would just be the variance, the conditional variance, as we've determined here. Okay, so let's just see, what did we want to accomplish in that digital office hour? We used the two-pass estimation to fit an ARMA 1.1 to some training data. We rely just on OLS estimation. Then we were forecasting the next two outcomes, and we quantified the accuracy of the forecasts. We also again saw that if the epsilons are Gaussian white noise, then the entire forecast will be such that the realized value will come from a Gaussian distribution. On average, our forecast is correct, and the uncertainty around the forecast is characterized by the variance.